Hi, I'm Ned, and I've started streaming. This is a recording from my live stream over on twitch.tv/NedMakesGames. I'm live most Mondays, Wednesdays, and Fridays at 10 a.m. US Eastern Time. I'd love to see you there.
Alright, I knew I forgot to do something, but okay, let's get started for real this time. Alright, yeah, so been a lot of changes in both my professional life and on the channel, because basically if you haven't heard, I got a full-time game development job, so for better or for worse, that means I can really only stream on the weekends. So normally I'd like to get started a little later, but I actually had some technical difficulties because I've been moving stuff around on my computer. But yeah, so I think that's all set up now. But okay, so let's get started. So today we're going to be doing something a little different. Normally I just do programming on stream, but I think I really want to get the new tutorial finished. So I want to work on the tutorial script on stream today. So if you've ever wondered how I create tutorials, then I guess this will be a good I guess look behind the curtain. Oh yeah, and sorry, I just noticed my microphone clipped there, so let me turn the volume down a little bit. Okay, yeah, so you can see this is just the script for the first part of the tutorial series, because I'm going to break it up into 3 tutorials, and you can see it's already 20 pages long. And usually about 10 pages is 20-30 minutes, so I kind of think this is already going to be an hour. So yeah, you can see there's going to be a lot of content in this series, so yeah, because this first part is kind of introducing how to write shaders, and then the second part is going to be about how to write or recreate URP's lit shader, which you can see. Well, this is actually the custom shader, but it's pretty much a recreation of the lit shader. If I can get it to zoom in, I always forget the keybind. Oops. Alt right click. There we go. And and then the third video will be about extending the shader with your own custom stuff, specifically custom lighting, which I can turn on with this. So yeah, this is, you grab the data from all the lights and you can basically use it however you want. It doesn't look that different because I kind of just did a normal lighting algorithm, but okay, I was clicking the wrong thing. Is this correct? Where? Oh, here. Okay, I just didn't. I don't like the custom lighting doesn't have alpha pre-multiply mode. Okay, so I guess that's what was going on. Excuse me. So yeah, if I turn this to custom lighting, it looks wrong because I don't have a pre-multiply mode implemented, which yeah, it's kind of beyond the scope of the tutorial. But anyway, okay, so what I wanted to do is kind of skim through here and see if there's anything I want to change. Because as writing it, I kind of think of other ideas. So this is just going over the introduction. It's like a list of supported features. The tutorial assumes you have knowledge, blah, blah, blah. Okay. So kind of what what I want to do with this tutorial is, I know that shaders have a lot of things you have to learn kind of up front before you can get anything on the screen. So what I wanted to try to do with this tutorial is only explain the bare minimum before you can get like data, or before you can actually get something on the screen. So, and then explain things as I go. So over here, like, I basically just show how to create a shader file. Okay. So you can open it in your code editor. So once you've opened it, yeah, so it has automatically generated code, so you can delete it. First line opens a shader block and defines the shader's name. Okay. Shaders are actually made of many smaller functions which Unity can invoke as needed. The first sublevel is called a subshader, which you use to define different versions to run on different render pipelines. Okay, define the settings and add a tags block. Subshaders are broken into several passes. For certain features like shadows and post-processing, Unity needs to render object in different ways, so that's what the passes are for. Okay, so the forward lit is the lighting pass. URP shaders are written in HLS cell, which are similar to a simplified C++. Okay, and to keep things organized, I like to keep HLS cell in a separate file. That's easy to do. Create a text folder called forward lit. Okay. It's actually my lit forward lit. Okay. Oh yeah, so what I wanted to add here is I did a poll a couple weeks ago, and a lot of people said that they didn't really know how to like think in writing shaders, if that makes sense. So the main thing is shaders aren't object oriented, so I did want to add a bit about that, but when would be the best time? Okay, so I guess now would be good, because what I'm going to do, kind of start explaining the different stages of the graphics pipeline. And yeah, so shaders have multiple functions. Okay, so when writing shaders, try not to think with the same programming strategies as you would for C# code. LSL is not object oriented. If you've ever worked with data-driven design, this is much more like shader code. Yeah, so you basically use functions to transform data into formats that you need. So take mesh data and transform it into pixel colors on the screen. Alright, so shaders have several let's see, so I'm trying to like segue into the vertex and fragment functions. I guess several places where you can insert your own code. Let's see, I haven't really talked about the graphics pipeline yet. So yeah, so here I'm talking about, I've already introduced like a shader pass, so I'm trying to So I talk about the vertex and fragment functions, and they kind of tell what they're for, which I think kind of feeds back into this. And then after that, I go into talking about each stage of the graphics pipeline. Let's see. So there are two standard functions that each shader pass must define: the vertex and fragment function. They transform data into different forms. The vertex function takes mesh data and transforms it onto positions on the screen, or this should be into, while the fragment function takes those positions and calculates pixel colors. They have several let's see. So yeah, so you can pass data between each other with the, I think I'll change this to graphics pipeline, but let's see. Around them is sort of new thought here. A system called the graphics pipeline, which simplifies data transfer between these functions, as well as calculating I guess calculating, I'm trying to like figure out how to talk about clipping. Some standard algorithms, which I'll explain soon. Okay. I don't know, the wording there is not perfect, but I'm just trying to get the data on the page for now. Okay, I guess I should say, yeah, every, okay, well I do. I was gonna say every pass can have its own, but two standard functions that each shader pass must define. I guess maybe each pass can have its own version of these functions. Okay, so don't really need this anymore. Let's examine each. Alright. The graphics pipeline can be divided into several stages. Let's take a look at each one. Okay, so the graphics pipeline controls how a mesh and material go from a blob of data to a picture on your screen. You can think of it as an assembly line. Each stage has a specific job, and the previous stage can pass data to the next through a data structure. Okay, so I feel like these don't segue into each other, because here I'm like, should go right into the input assembler, but I have this. I think this is good information though. Maybe I can just put this right here. Okay, let's see. So around them is a system called the graphics pipeline, or maybe they should say these are part of a system. These are part of a system. Or maybe I guess that's fine. The graphics pipeline controls how a mesh and material go from a blob of data to a picture on your screen. Okay, so this pipeline is invoked by the renderer whenever it must draw a material using your shader. The graphics pipeline controls how a mesh and material go from a blob of data to a picture on your screen. Think of it like an assembly line, which can be divided into many stages. Each stage has a specific job, and the previous stage can pass data to the next through a data structure you can define. The vertex and fragment stages are called programmable, meaning you can write the code that runs during that stage. Okay. Alright, so let's start at the beginning. The input assembler gathers data from the rendering mesh and packages it into a structure for the vertex function. You can define the structure and decide which data you need the input assembler to gather for you. Okay, so I keep debating about whether I should explain this more, but at the beginning of the tutorial I explained that you should already kind of know what a mesh is, so maybe I should get some examples like position in normal vectors. What's it not like about that? No. Maybe it should just be a comma. I don't know. I guess the grammar doesn't really matter. I'm going to be reading this out loud. Okay, let's see. Here's input struct for our forward pass. Okay, it should be an input struct. Define the structure called attributes. Position is a vector 3 or a number made of 3 floats. In HLSL, vector 3s are written as float 3. You can name the field anything. Let's go with position. To tell the input assembler that this should hold vertex position data, add this keyword called a semantic. These semantics are used throughout HLSL code to tag variables, which are used in a special way by the pipeline. This one tells the input assembler to fill this field with vertex position data. Okay, so next up is the vertex stage. As mentioned before, this stage is programmable, so we need to write it by defining a vertex function. Defining vertex, our function HLSL is similar to C#. The return type goes first, void, function name, a list of arguments. Okay. The vertex stage must calculate where each vertex on the mesh is positioned on screen. Since the attribute structure only contains data for a single vertex, the render pipeline will call the vertex function multiple times to compute screen positions for all vertices. Mini will run in, let's see, many calls of this function will run in parallel. Let's see, I guess that's best. I don't know. If you've ever worked with multi-threading, you know that parallel processing can introduce a lot of complexity. Shaders bypass much of this in two ways. Oh yeah, I wanted to rewrite this little paragraph, but shaders cannot store state data. That's kind of, so that's like not true, but it's like a vertex function can't store data that it would access the next frame. Let's see. Okay, let's see. Programmable stages cannot store state data. All the data they work with is set before any function, or let's see, before the graphics pipeline even starts. It prevents race conditions. The programmable stages are given as little data as possible. Okay, well this doesn't really have to do with multi-threading. It's more for caching, but okay, bypass this by preventing programmable stages from storing state data. Okay, I guess I should, and let's see, and then to improve performance, each, I guess, vertex function is given as little information as possible. For instance, it only receives data or vertex data for a single vertex and cannot read data for any other vertices or even know how they're connected. Okay, yeah, and then there are some ways to get around these restrictions, but let's play nice for now. Okay. So, I feel like this is kind of important to know for shaders because I feel like when I first started writing, this was, I guess, a big gotcha point because you kind of assume that you can access the whole mesh at once, but you really can't. But I don't really know if this is that useful at this point or not. I guess I'll just leave it in for now. Okay, so with this in mind, we need to compute the screen position for a certain vertex. Given to us in the attribute structure, the position is currently in object space. Yes, now you can kind of see like what I mean by having to explain so much before we can get anything on screen, because now I have to talk about object and world space, and we haven't even got to the fragment stage yet. But anyway, it's another name for local space if you're used to Unity's scene editor. Okay, so we need to convert them into clip space. Yeah, I kind of sidestep explaining it. it's not really needed. Okay. The include command tells the shader processor to read the file located at this location and copy its contents onto this line. If you're curious what's inside, you can open it yourself from the packages folder. Included files can include many other files themselves, leading to a kind of tree structure. For instance, lighting HLSL will pull in many helper functions from across the entire URP library. One such function is get vertex position inputs. Okay, yeah, and I'll probably show this on screen, but it basically just outputs a structure with clip space. Okay, and note that clip space is in float 4. If you try to store it as a float 3, Unity would give you a warning that data will be truncated. That's a common source of bugs, so always heed these warnings. And again, I don't really explain why it's a float 4, but I don't really feel like you need to know what clip space is to write shaders, at least this type. I don't know, if I ever do screen space, I guess you'd need to, but yeah, let's just keep things simple. All right, so keeping track of which space a variable or a value is in can get tricky, so URP adds a suffix to all position variables indicating which space the value is in. Oh yeah, so this is just a nice little programming pattern. So now we need to output the clip space position for the next part of the graphics pipeline. To do that, define another structure called interpolators, which the vertex function will output. We'll explain the name soon, but for, well, it's not really, it's kind of later in the video. Add a float 4 position CS variable. Okay, and now we have to add the SV position semantic. Okay, so the vertex function returns the interpolator struct. Declare a variable of interpolator's type. Okay, so it's just telling you how to declare a structure and then set the field. Okay. The vertex structure is, our function is complete, and then we go to the rasterizer. So it takes all vertex screen positions and calculates which triangles in the mesh appear, I guess, over which pixels. If a triangle is entirely off screen, let's see, the pipeline is smart enough to ignore it. Let's see. The rasterizer then gets data ready for the next stage of the pipeline, the fragment stage. The fragment stage is also programmable, and it runs once for every pixel. Okay, so it runs for every pixel with a triangle over it. Once for every pixel, the rasterizer determines, contains a triangle of our mesh. It calculates and outputs the final color each pixel should display. But of course, one at a time. Yeah, and so people that know a bit more about shaders will know that this isn't technically correct, because the fragment stage can run multiple times for a pixel, or even for pixels that don't contain the triangle sometimes, but it's good enough for now. The fragment function, which runs during the fragment stage, should look like this. It takes in an interpolator structure, which is the output of the vertex function. The values inside have been modified by the rasterizer. Position CS no longer holds clip space positions, but rather this fragment's pixel position. I wasn't sure if people would know what this meant, but it's not really important for our current stage of the shader, so I don't know if I should explain more. Maybe I'll put on screen. That's probably a good idea. I'll put it on screen because like clip space positions are bounded from 0 to 1 and pixel positions are, it's like counting each pixel assigned an index. So yeah. Okay, so anyway, you can pass other data from the vertex to the fragment function through the structure, which we'll investigate later on. The fragment function outputs a float for the color of the pixel. Colors are float fors because they contain a red, green, blue, and alpha value. To set the pipeline, or to let the pipeline know that we're returning the final pixel color, tag the entire function with the SV target semantic. Okay, so let's color all pixels white. Okay, that's fine. There's one last thing to do. We need to register our vertex and fragment functions to the shader. Okay, so yeah, now we're just adding the pragma files, or pragma lines. Okay, well first it's doing the include and then pragma, okay. Okay, so yeah, we had to do all that to get a white circle on the screen. Okay, so that was like 3.5 pages or something. Okay, so now I go on to text. Oh no, now I do colors. Oh yeah, because this explains properties. Okay, well let's just keep skimming this. I knew I wanted to make some edits up here to the part with where I explained it's not object oriented. So hopefully I made that a little more clear. Like I said, it's a balancing act trying to make explain everything, but then also, you know, not make there have to be 30 minutes before I can actually start coding things, so. Okay, so anyway, we have a flat white circle. Shader properties are essentially variables that can set and edited through Material Inspector. They allow objects using the same shader to look different. If you're wondering what the difference between a shader and a material is, a material is just a shader plus set values for all of its properties. Well, there's a little bit more as well, but we can define properties inside the shader file with a properties block. Yeah, it's kind of a weird syntax. Okay, so I was just saying how to do the color property. Alright, so that's good. So for textures, we first add a texture property. Okay, and then you can add this main texture attribute to make it work well with materials. Okay, UV offset multiplier. HLSL side of things. Okay, so here I have to explain what a macro is. Texture 2D here is not a type of something called a macro. You can think of macros similarly to functions, except they run on code text. You can define them yourself using the define command. The precompiler will look for any defined macros and replace the macro with the defined text. Copying any past arguments. Here are some examples, so then I'm going to show some. They're useful in shader code since HLSL does not have inheritance or polymorphism. For instance, if you want to work with any structure that has a position OS field, but you don't necessarily know the structure type, a macro can do the trick. Okay, so yeah, that's good. I guess I'd show an example. Oh yeah, so then I talk about why we have to use a macro here, because DirectX and OpenGL have different texture types. So in order for your shader to run on both, Unity has a bunch of macros that you can use. Okay, so then I talk about the scale and tiling. Oh no, I'm talking about the sampler, okay. And yeah, then the scale and tiling variable. Texture is taken care of. You can sample it in the fragment stage. Wait, did I talk about how to get UVs? Oh, I guess that's coming up later. We like to sample it in the fragment stage so we can apply the texture to the model per pixel. We can sample a texture using the sample texture 2D macro. Yeah, so now I'm saying, however, we don't have access to UVs yet. Yeah, and I'm not going to explain UVs. I just kind of assume you already know how to do that. Okay, so we can't grab them out of thin air in the fragment stage. They're defined per vertex on the mesh, meaning that we need the input assembler to gather them for us. Okay, so then telling you how to add it to the structure using text chord 0. The attribute struct is not available in the fragment stage, so now we have to pass it to the interpolator struct. Okay. Okay, so I'm trying to explain the transform text. I guess there's a lot to go into it, so it's always a good idea to do as much as possible in the vertex stage, since it usually will run fewer times. Okay. Provide a cool macro to apply it. You can see the code here. There are two interesting things about this. First, the double hash tells the precompiler that it should append whatever comes after to whatever is passed as an argument. Okay. Yeah, that's like, it says, it's like texture hash st in the macro, and then it like replaces this with color map. Okay. Oh yeah, and then I kind of explained swizzling. It's called swizzling. You can ask for any combination of the X, Y, Z, and W components. The compiler will construct an appropriately sized float vector for you. Do I talk about the W? Because I don't think it's really obvious that W is the fourth component. Oh yeah, here I do. And yes, the fourth component of a float 4 vector is called the W component. Okay, so now we have the UVs in the fragment stage. Okay, yeah, now I'm explaining how the interpolator, or how the rasterizer interpolates. The vertex function outputs data for each vertex. The rasterizer takes those values, places the vertices on the screen, and figures out what pixels lie in the triangles formed. So yeah, that's what value will UV have. So any field tagged with a text chord semantic will be interpolated by the rasterizer using barycentric coordinates. Okay, that's good. Keep in mind that the values in the input structure are a combination of values given by the vertex stage for 3 vertices making up the triangle. Okay, this sentence is a little long, but I'll come back and rewrite it at some point. Okay. Alright, so yeah, so I note that we are doing transparency later. Alright, so now lighting. Okay. So far we've learned how to write unlit shaders. They're very important, or obviously lights are important. URP's lighting file, there's a function called universal fragment blendfong, which calculates a standard lighting algorithm called the blendfong shading. Let's see, the fragment function return. Okay, it takes many arguments but bundles them up into 2 structures. Oh yeah, and there was something annoying about this, because in Unity 2020.2 or 2020.1, it doesn't have the version with the surface input, so I had to write this fork here. But I guess it kind of serves as an introduction to using these, so it's not a huge deal. Okay, so we cast 0 to structure type. Oh yeah, so here I talk about the differences using hash f. Okay, that's good. Scene editor of a black sphere. You can set the albedo field in the surface data structure. Okay. And some data in the input data struct. Okay, That's now we have to get normal vectors. Okay, so world space. Okay, so now we have the normal end position in the fragment function. Okay, yeah. Okay, so now, oh yeah, there's no specular highlights, so we need to calculate a view direction. Okay, yeah, and then you see there's still no highlights. Wait, okay, so I kind of double explain that. Let's see. There's still no highlights though. Highlights depend on a vector called. Okay. Okay, so I'm just saying also called specular lighting. Maybe we should just move this up here. Okay. So yeah, inside it uses a hashf command internally to toggle highlights on and off. So we have to define a keyword. There we go. So now here's the first time we've used a keyword, so I have to kind of explain that. Shaders make extensive use of keywords to toggle on different functionalities. So there we go. Okay, now I have to talk about smoothness. Oh yeah, and then to make things more confusing, 2020 and 2021 handle the smoothness differently, but it's not a huge deal. Okay, and then I go into shadows. Okay, and then I kind of, yeah, so now we have to introduce shader variants. Variants of the shader, variants of the forward lit pass. Multi-compile can also take a whole list of keywords, in which case it will create a variant with each keyword enabled. Okay, so variant with one of each keyword enabled. I think this will be a little, I'll have to put a little visual on the screen as well, but okay. Materials automatically choose the correct variant for the situation at hand. If you want to use a variant with the main light shadows defined, simply call enable keyword on the material instance. URP does this automatically if it detects a directional light in the scene. Okay. Using the system, we can also easily support variants with and without shadow cascades and soft shadows. That's good. Still another version difference. Oh yeah, so Unity URP are 2020 and 2021 have different, because yeah, so this one in 2021 that it has a multi-compile with one of each, but in 2020 you have to have both of them enabled, so you have to do two different multi-compiles. Okay, so then we test it out. If you ever need to know which shader variant is currently active, okay, then I should introduce the frame debugger. Okay, so that's good. So now cast shadows. Yeah, so now we have to introduce a second or more shader passes. On our side, the shader caster pass will be contained in its own HLSL file. Okay, and then I kind of go on this thing where I try to introduce the guard keywords. Okay, it's a new shadow caster pass. Okay, blah, blah, blah. Okay, new HLSL file. Okay, so now it's talking about biases. Oh yeah, and then I have to talk about the near and far clip planes. Okay. Back in the vertex function, we return the output structure. So now we need to add. Okay, so now we have to add the pass to the shader lab file. Okay, so we need to tell Unity a bit of information about the pass to make sure it runs smoothly. Oh yeah, so now we're talking about the Z-write tags. Yeah, these ones. Okay, no, it was right before. You're not helping me out there, Google. Oh right, and I have to talk about the depth buffer a little bit. Okay. I'm pretty sure that all this part is fine. I guess let's still skim it though. Okay, so for transparency, I talk about blended and cutout transparency. First, we implement blended transparency by adding the blend command. Okay, and then Z writing on and off. Okay, and then I have to talk about the transparent render queue. And then I talk about how you can have your shader switch between transparent and opaque using a editor script. Okay, yeah, so this is all about the editor stuff. Okay, and then I talk about alpha cutouts. And then culling. Okay, and then here we talk about SRP batching. All right, and then a little bit about shader targets. Okay. All right, so I think it's already taken about an hour to do that. All right, so let's see what we can get done for the second tutorial. I won't worry about writing this intro because it's probably gonna be about the same. So I'll just remind myself. So the first part, I have kind of this outline of the entire series, and the initial video did this bit. Actually, it's more like that, but okay. So now the next part, we're gonna do PBR lighting, which is what does this? Okay. Oh, we're gonna switch to the instead of using universal blend Phong, we're going to switch to. If I can find it. The universal fragment PBR function, and I think. Oh yeah, and then it should just show some way to debug because the PBR lighting has like debug visualizations, so we can add a few of them. Oh yeah, and in order to do that, we have to talk a bit about the textile size. Okay, and then we have normal maps, metallicity, and then the specular workflow. We already handled smoothness actually, but I guess we'll have a smoothness texture. Okay, and then yeah, more transparency modes, emission, more lighting. Like we have additional lights, cookies, light layers, more shadows, and then baked lighting, which is going to be a big section because we'll have to add the meta pass, light map support, shadow masks, light probes, reflections, occlusion, and then the visualizations for debugging. And then depth pass, depth normal pass, green space ambient occlusion, fog, decals, and then stereo eye support for VR. So that's all in the second video. And the third video doesn't have as many little numbers, but we're going to do custom lighting, and then some more optimizations, and then more extensions that you could add to it. So basically, yeah, this video might be, well, I mean, I'm going to have to explain basically how to re-implement the PBR lighting algorithm with your own custom lights, but okay, but let's get started on it, on the second part. Okay, so how I kind of do it is, while I'm writing, I also go through and I have like these projects where I implement the tutorials step by step. And the reason I do that is because I want to kind of make sure that the shaders work during every stage of the tutorial. And that's extra difficult for this specific tutorial because I wanted to make it work in 2020.3 and 2021.2. So I have to do it in both versions at once, but we'll make it work. Okay, so what I should do, I think I already committed everything. Yeah, I don't see, it's all green checks. So what I can do is kind of copy stuff from the master shader, or like the completed shader here, into this, and let's see how it goes. Okay, so what I want to do, so I guess pretty much all I have to do is copy, or is like change the universal blend Phong to universal fragment PBR. Okay, so let's try that and see what happens. Alright, so yeah, I can get rid of this now, I think. This is, okay, the 2020 version. Okay, we don't have fog yet. Yeah, we don't even have this color variable, so we'll just return. Alright, let's see. Okay, yeah, so it looks basically the same, but no errors. So is that all I have to do for that, I guess? Okay. And then next, so for debug visualizations, it's only in 2021. Okay, so let's add it here. bugs here either. I don't see specular highlights on these though. Did I turn it off maybe? Oh, it's because it's using different smoothness values now, I think. Okay. So this material is using the Unity's default shader. Oh yeah, the specular highlights work here. Okay. But they're not working here. Because you can see a highlight there, but it's not showing up on the custom material. So let's see if we can figure that out. Still have specular color enabled. Alright, well, let's look inside Unity's lighting functions and see if we can figure out why it doesn't want to do specular highlights. Oh, this is wrong. It's in the shader library. That would be this lighting physically based function. Okay, it should work. Because the specular highlights off is not defined. Yeah, I guess we don't even really need the specular color, so I should probably delete that, but let's see. I wish I could highlight this easier. Okay, so we just pass it through. It's strange they like calculate it twice. Oh, it's backwards compatibility, okay. Alright, well let's... I don't think this will matter, but I'll just delete that because we don't need it anymore. Let me remember that I did that, so delete the specular highlights. Define. Still works fine here. Oh. Okay, I guess it was there. It's just okay, I just didn't see it. And then if we put it super high, oh, yeah, I just picked bad values, so that was my bad. Well, that's good, I guess. Yeah, because we don't have to change anything. All right, so that's pretty much all we have to do. Okay, so so far we've let's so far we've been using the blend Fong shading algorithm. It's great for simple lighting, but if you have more complex materials, it's difficult to shade them correctly. Most rendering engines have created a standard shading algorithm called PBR, or physically based rendering. This tries to emulate realistic lighting of more I guess a wide variety of materials. Unity URP makes it easy. Let's see. Not coincidentally, this is the algorithm the standard lit shader uses. Luckily, it's as easy as switching out the function we call in the fragment stage. Let's see. It's easy to implement PBR in your own shader, or at least a limited version of, well, no, because we're going to do a full version of it. Let's see, just switch out the final function we call in the fragment stage to universal fragment PBR. It even takes the same arguments in 2020 and 2021, so we can remove the hash if statement. It also has specular lighting by default, so remove the hash define in the shader file, the .shader file. Okay, so let's see. In the scene view, things will look very similar, although if you're using Unity 2020, you should lower your smoothness to a value between 0 and 1. In fact, let's enforce that in the inspector. In your .shader file, change the smoothness property to be a range type with bounds 0 and 1. Now the inspector will render a slider and clamp the value accordingly. All right, so yeah, let's add that real quick. All right, okay, and if I had done that, I probably could have noticed what had gone wrong before, but it's not a big deal, whatever. Okay, PBR rendering supports some other special material inputs like metallic and emission maps, which we'll implement later in the tutorial. First, though, let's take a look at Unity 2021's new debug views and see how to, I guess, replicate them or a little bit in 2020. Okay, so before I do that, let me just commit the changes I've made. So commit, so PBR, and then what I want to do is create a tag. So I'm on number 9. So 9.1 PBR. Okay, and so that tag will let me switch between these different versions as I need to. And that's kind of how I keep multiple versions of files for the tutorial. It works pretty well unless I make a mistake and I have to go back and change stuff, but that doesn't happen so often. Alright, so now what I need to do is add debugging support. Okay, we could get, I mean, there's a lot. Okay, so we won't do this because we don't even have normal maps yet. Okay, well, let's do like a simple version and see what Unity will even display. Okay, so there's no reason to do this in 2020 because yeah, this stuff is only in 2021. Okay, so we do. Actually, it goes, it's just lighting input stuff. So go here. Alright, I'm gonna, my IDE doesn't really like to indent this kind of thing, but okay, we don't have light maps, so we can get rid of that stuff. So pretty much, I guess we'll just have this texture data and then the clip space. I'm not sure what views that will enable. And then to do that, I also have to add the bitmap data for this color map. So these are more kind of magic values that Unity sets automatically, kind of like it does with the scale and tiling for the color map. The textile size, well, I don't even remember really exactly what these values do, but this kind of tells you, oh wait, the textile size, yeah, this is like, it gives you the size. The X and Y is the size of one UV, or I guess one textile in UV space, and a textile is a pixel on the texture. And then the ZW gives you the size of the entire color map texture. And then MIP info gives you like map information for this texture, which can sometimes be useful. But I pretty much only ever use it for this debug view. Okay, and then the setup debug texture data basically does a lot, or grabs a lot of information from us, or for us. So that should be good. And then we can go in the, let's see, what's it called? Yeah, analysis, a rendering debugger. Okay, so a lot of this, so the albedo does not work because it's still doing shading. Oh, because I need to add the multi-compile pragma. Unity really doesn't know how to, or Visual Studio really doesn't know how to format these shader files. Okay, yeah, there we go. So now it's albedo and specular color. Yeah, so image inclusion and emission we don't set. It still sets, or gives us world space normals. Okay, no tangent space though, because we don't set up any tangent space stuff. Okay, so we can't do lighting complexity yet. I don't know why that is. Okay, sprite mask, we don't do sprites. Just kind of seeing what works. Okay, so this lets you find like values that are within this range. Yeah, most of the, okay, that does work actually. But yeah, some of these values won't work yet because we don't have normal maps. Okay, but a lot of it does work. Where was the... didn't even see, I don't think it even uses the map stuff, does it? Or maybe it's part of... It says there's overdraw there, but these are both opaque. Oh, it's probably just the way it gets sorted. I just thought it would give, like, I don't see anything about mip-maps, so I'm not sure if it even uses the mip-map stuff that I just sent into it, but I guess I can see what stops working. Okay, well, I guess maybe it's used for something later on. I don't know. Okay, and the lighting complexity probably doesn't work because we don't even have additional lights enabled, so there won't be any. Although I do kind of want to make sure that it works on the completed shader. Window. Okay. Wanted to make sure. All right. So we didn't really do a whole lot. But I want to add what I did add to the 2020 version. Oh. Okay, what else? Oh yeah, I added this pragma. Okay, I think that was it. Yeah, because I pretty much just added. Yeah, okay, that's good. Okay, yeah, so here nothing should have changed because all that stuff is only in 2020.2, but I did want to at least show people kind of how they can do it in, or it was in 2021, how they can do something similar in 2022, or in just 2020. So probably what, instead of returning this, you could just return input dot normal world space, which is usually something I usually do. Oh yeah, but it's a float 4, so we would have to do something like this. So now you can get normal vectors. I really do like the new visualization though, so you don't have to go in and edit your code like this, but did want to at least show people that that's possible. 'Cause I think that's kind of another thing with shaders that people don't realize is basically everything is just data. So you can do whatever you want with it. You can output a normal vector as a color if you feel like it. Okay, so let's add a little bit of information about this. So Unity 2021 has a new feature called the rendering debugger. Using this, you can easily inspect multiple aspects of your materials and lighting without having to edit your shader. Already, just switching Mylet should support many of these views. Check it out. Some others will require special inputs in the shader. Thankfully, it's not difficult to add them. In your forward lit pass, the input data structure contains several fields only used for these debug views. Fill them only. Okay. For instance, some views need clip space position. If but we only need to set this if debugging is active. Similarly to main light shadows, URP automatically enables a keyword when debugging our debug visualizations are active. Use an if command to only set the clip space position if needed. Okay. Oh, well, that's not true, actually. I just always set it. I guess it doesn't really, yeah, the compiler will just strip this out if it's not used. Okay, so the problem is this is only visible, or this is only there if we're in this version. Okay, so, but this field only exists in 2021.2 and later. Only set it if the Unity version is equal. Okay, matches, I guess. Similarly, the debug views can. I don't know how to do this because like they asked for this data, but I don't know if it's ever actually used. But I don't really want to just take it out because I'd like to keep this future proof. Excuse me. I think I caught that one on the mute. So I'm trying to think about the best way to say this, like, okay, because I think adding this isn't actually going to enable any more displays as it is. I guess I'll just say that. Also, even though it's not exposed in the debug or the rendering debugger right now, it does ask for some information about our texture. About our main texture, if this, but we only need to set it if debug visualizations are active. Keyword signaling this. Use an if def command. To call this macro if needed. And to support it, we need to ask Unity for some more texture information. It will set these to, okay, let's see. In my lit common, add 2 new fields to the property buffer. Unity will set these automatically like it did the tiling and offset field for the color texture. This one holds the size of the texture in pixels as well as the size of one texture pixel, so known as a texel in UV base. The second one gives bitmap information. If you'd like to learn more about bitmaps, check out my tutorial series on them. Okay. Regardless, you should have a couple more debug visualizations available now. If you're stuck on 2020.3, you can't make use of this feature, but you can output your own visualizations very easily. For instance, this normal visualizer is very useful. Let's see. So let's see. I guess red error values point in the positive x-axis, green the y-axis, and blue the z-axis. You can get something similar in 2020.3 by outputting the normal as the final fragment color. Okay. Just remember to add a 1 in the W component for alpha, which you can do with this constructor. Remember everything in shaders. I guess not everything, because texture is technically not. Just about everything in shaders is just numbers. You can easily output them as the final fragment color. Use that to help you debug if you are seeing unexpected results. This is correct. So just about everything is just numbers, or it should be just about everything are just numbers. I don't know, neither one sounds correct. Including colors. You can easily output whatever you want as the final fragment color. Use this to help you debug. Maybe this should be first. I don't know. I mean, using the frame thing is kind of, I wonder. For a normal, or for someone who hasn't worked with shaders, if they were given this view and told it corresponded with smoothness, I don't know, would they understand that 0 is black and 1 is white? I guess, well, I already said that 111 is white at the beginning of the tutorial. I mean, I guess I could show myself doing this in the video. Let's see. I kind of think this should go up before I even do it. Technically, I could have put this in the first video, but the first video is already long enough. And yeah, we're not really doing much debugging then, because this is kind of simple stuff. But now we're actually going to be doing with more complicated materials, so I think this is more useful. First, though, let's since we're going to be working with more complicated materials and lighting, let's investigate some good techniques to debug them. So, for instance, it's very common to need to visualize a mesh's normal vector. One way, okay, I guess I gotta kind of flip this around, is just to output the normal vector as the final fragment color. When reading this on the, when viewing the results, you can interpret redder values pointing in the positive x-axis. Any negatively pointing normals will be black. So if you also need to view them a little better, try rescaling them to range between 0 and 1 by having and adding 1. This will give, just remember that I guess a half red vector now corresponds to 0 on the x-axis instead of black. Okay, here I do the same with smoothness. Okay, so then it'll show me back and forth. Okay, and then Unity 2021. Okay, I guess I could just hop right into this. Has a new feature called the rendering debugger, with a bunch of debug views automatically. You can easily activate without editing your shader. Let's see, you can expect a wide. Okay, I guess it was fine before. Okay. That's what I need to ask. Just stick to the old-fashioned method. Okay. All right, so that's done. Let's see what else, or what's next. Okay, so normal maps. Oh, I guess before I start, let's save all the stuff I've done here. Debug views. So I think this last one was 9.1, so it should be 9.2. Debug. All right, so for normal maps, pretty much, really I only need to explain tangent space. Okay, but let's see. Okay, I also have to define this. Okay, but only for the debug view, but let's go ahead and do it anyway. It's not a shader variant, but okay. And then the mylet forward pass. Okay, so I have this apply normal map function, which I guess is kind of makes things a little simpler. And then we actually calculate it here. And then I need to set the tangent to world. And for some reason it needs... Okay, and the surface input for some reason needs tangent space normal, which I've never really understood. But maybe it just does it for the debugging, I guess. Let me just make sure that's how it worked. In common. Yeah, so just right there. Oh yeah, and then I need to use not the value from the input anymore. And then of course I need to add the normal map to the properties. Okay, it should go in between these two actually. All right. Unpack normal scale. No matching two parameter function. Oh, I didn't. Okay. I need to add the normal strength here. Valid subscript tangent world space. Oh, I need to get tangents into the fragment function. Okay, so to do that, I just need to... Okay, so there's more changes here than I remembered, but not that big of a deal. And then the interpolator, I need to pass the tangent space, or the tangent vector. And then in the vertex stage, I need to call this variant with a tangent. So it will also calculate or give me a tangent vector here. I think that's it. No. Oh, I need to add the normal map up here. Still more. Unexpected token return. Oh, I forgot the semicolon there. There we go. Okay, so now let's add. Do I have a simple? No, I don't have a normal map yet. Let's grab this one. Just has a simple bump texture. So I need to tell Unity it's a normal map. And okay, so one thing I like is Unity has this you can tell the default texture, you can put bump here and it'll just give you the normal map like neutral color, which is nice because sometimes before if it's set to white it makes your shader look really weird if the normal strength is anything but 0. But then I could give it a test normal. Okay, there we go. We got some nice bumpy lighting. Let me put it on the other one too, I guess. And maybe this one. Okay, I don't even have a custom shader for it. That's fine. Let me just make sure that Shadowcaster still working fine. Oh, there we go. Or I guess I could already see because the Shadowcaster is right here, and then it's still receiving shadows. So yeah, that's fine. Okay, so I think that's it. So now I can add everything to the 2020.2 version just by copying and pasting stuff. Don't need that anymore. Okay, and then I don't have the texture here. Just copy and open this. Okay. Okay. So, fortunately, I'm about out of time, but I kind of want to write down what I had to do here. So, we had to. Oh, okay. Well, before I go, I should make sure that the debug views for our dealing with normal map works correctly. We've got tangent space normals, world space. Okay, that's not right because it's still showing the bumps. I thought that's why I had this define. Oh. Okay, no, that's right. This is right because it's the normal and world space. Yeah, if we want the vertex normal, we just gotta do this vertex attribute. Okay, so that's fine. Yeah, I was just misinterpreting it. What about that? Still doesn't work, but lighting without normal maps. Okay, so this does work. Okay, so it's good. So got to add define and dot shader. I don't need bold anymore. Then we need tangents and vertex and fragment, normal map and normal strength, properties and fields and common file. Then the apply normal map function. Then of course we gotta explain tangent space, add tangent space normal to surface input, add tangent space matrix to input data in debug mode. I guess this kind of goes with that, so that all everything. I guess I could check here. I guess I really don't have to do this because I can just say compare with unmodified version. Okay, but I think that was everything actually. Okay, well, I think that's about it for the stream. But you can see we worked for 2 hours and we pretty much, well, I guess we did go through the entire first video and add some stuff to that. But you can see kind of why this takes me so long is because there's a lot that goes into writing these scripts. So, but hopefully I'll have some more time to work on it over the week, and next weekend maybe we can finish up the second video script because I want to finish all the video scripts before I start editing any of them, because I kind of want to make sure that I don't want to move things around, because I'm kind of treating this series as like one big video instead of 3 separate ones, because I think I've kind of made the mistake of not doing that before, and the series I think suffer from it a little bit. So I'm trying to avoid that problem this time around. But yeah, thanks everybody for coming by. I hope that this kind of writing the scripts isn't too boring, but we'll get back to programming soon. But I'll be back next Saturday. I'm going to try to start a little earlier, but I should for sure be live by around 11 Eastern, US Eastern time. So I hope to see you then. If you enjoyed the stream, I'll put some links in the chat if you want to connect with me on social media. Otherwise, yeah. Have a great week, and I'll see you Saturday. Bye bye.